Hello everyone. In this video, I'm going to be discussing about Turing Machine and a movie about Alan Turing called The Imitation Game. So let's start with the Turing Machine. So back in the 1930s, there was this question that mathematicians were trying to answer, and that is how much math can we do just by carefully following a set of instructions. So this question is not just about any mathematical equations. It's about understanding the limits of computations. And this is where Alan Turing came in and invented a theoretical model which is now known as the Turing machine. So the Turing machine helps in solving this problem by showing how any problems can be solved just by using a precise step-by-step process while also showing what problems can be and cannot be computed no matter the time and the memory available. This helps us understand the boundaries of what is possible through algorithms alone. A Turing machine is not a physical machine, but an abstract concept that simulates how a computer could process data one step at a time using a predefined set of rules. A Turing machine is formally defined as a seven-tuple machine, where Q is a finite set of states, sigma is the input alphabet, which consists of symbols in which the machine takes as input, and the gamma, which is the tape alphabet. It includes all of the symbols from the input alphabet as well as a special symbol called the blank symbol. Next is the delta, which is the transition function, which takes the current state and the current value or the current symbol of the cell and outputs the state in where we will transition in and the new value of the cell as well as the direction to which the head will move, which can either be left, right, or it can also stay at the same position. So next is the Q0, which is the initial state, and the halting state, which is for classical model, and the Q and the accept and reject state, which is included for the modern model. So what's the difference between the classical and the modern model? So in the classical model, we have one halting state, which indicates that the machine has stopped running, but it doesn't indicate the reason to why the machine stopped running, whether it was successful or a failure. So for the modern model, we have it explicitly indicates whether the machine was successful or a failure, unlike the classical model. So moving on, the Turing machine consists of a data structure called the tape. It extends infinitely in at least one direction. It is divided into cells, and each cell can contain one symbol from the tape alphabet. So an empty cell is represented by a blank symbol. There's to traverse or modify the contents of the tape. We will use a tape head. A tape head can move either left or right, one position at a time. It can also write or modify the current cell. And there's also something that we call the state register, which stores the current state of the machine. So here I prepared something to visually illustrate how a Turing machine might work. So I included here a state machine which defines the behavior of the tape head. So let's start. Initially, the state stored in the state register is the initial state, which is Q0. So we take the input from the tape, which is 1. It is where the tape head is currently pointed at. So using So using input 1, we will transition to Q1, and with the output of 0, so we'll change 1 with 0 and move the tape head to the right. So next, we're at Q1, and we take the input again from the tape, which is 0. Then we'll transition to Q0, and the output will also be 0, so it will remain the same, and move the tape head to the right again. So now we're at Q0 again. So we take the input from the tape, which is now 0. So using input 0, we'll transition to Q3 and output 1. So we'll change 0 with the output, which is 1. Then move the tape head to the left. And now we're at Q3. So the input symbol now is 0. So using 0, we'll transition to the halting state, which is Q4. And the output will be 1, so we'll change 0 with 1, and will stay, and the arrowhead will stay at the same place. And that's it for my illustration. So here are the variants of Turing machine. So first is the two-way infinite tape Turing machine. The tape in this Turing machine extends infinitely to both direction, which is left and right. And this enables unlimited spaces in both direction, which helps in avoiding boundary issues. Next is the multiple tape Turing machine. So as the name suggests, it consists of multiple tapes, each having their own tape head which operates independently. So this is very useful for um, speeding up the computation because we can use it for parallel processing. Next is the non-deterministic Turing machine, where for one single input and current state, there can be more than one possible transition, making it useful for solving problems where multiple paths and solutions need to be considered. Next is the multidimensional Turing machine, where instead of having to only move left or right, the head can also move up and down. It is very useful for problems that are spatial, such as image processing or grid navigation. Next is the multi-head Turing machine, which is just a regular tape which consists of multiple heads that operates independently. So this enables faster computation and more efficient operation without requiring extra memory. Next is the offline Turing machine, a multi-tape Turing machine where some tapes are read-only. So typically it consists of two tapes. The first one is the input tape, which is the read-only tape. And the second one is the work tape, which is the read and write tape. So it's useful because it separates input from computation, which reflects real-world algorithms. And lastly, we have the multi-track Turing machine, where each cell contains multiple track or multiple symbols, which allows the machine to read write multiple data pieces in one position. Why is the Turing machine an ideal model for modern computers? First, it supports universal computations. A Turing machine can simulate any algorithm that a modern computer can run on. Second, its simplicity and abstraction makes it easy to understand. With just a tape, a head, and a set of rules, it can perform complex tasks. So third, it shows logical similarity to computers. The way it reads, writes, and changes states is similar to how programs process data. Next, it provides a strong theoretical foundation for computer science. helping, helping us understand what can or cannot be computed. And lastly, it's independent of hardware, focusing mostly on logical computation rather than specific technologies, making it a timeless model for all computer systems. Now, let's move on to the second part of my discussion, which is about the imitation game. One of my favorite scenes in the movie is when Christopher finally managed to break the enigma. It's a very powerful scene because it captures the moment when a machine finally was able to solve a real world problem faster than any human could ever have. This moment not only showed the result of the hardship of Turing and his team, but also highlights the power of machines. Christopher, or the bomb, which is commonly called in the real world, was built to automate the process of testing a huge numbers of Enigma settings, which would be usually impossible for a human to do manually. So, from the perspective of automata theory, it's interesting because it shows how abstract ideas can give birth to something that is real, practical, and is capable of changing the course of history. The movie also mentions the concept of a universal Turing machine. It's a theoretical machine that can simulate any other Turing machine. It does that by reading M, which is the description of another machine, and interprets it as instruction, and W, which is the input for that machine. It then simulates how M would behave step by step given the input W. By doing so, it produces the same output that M would produce on W. It's showing that a single machine can compute anything that any other Turing machine can, which is the foundation of programmable computers today. Overall, I think the movie was very good and insightful. It gave me a deeper understanding for the concept of automata, especially the way it illustrates how machine could follow rules to simulate human logic and decision making. The story of Alan Turing helped me understand that automata isn't just a theory, but it can also pave the way for real world innovations that solve complex problems. And that's it for my presentation. Thank you.